Hello and welcome. My name is Thomas, and in this episode I'll be looking at challenge number 10, recovering a Cleartext document. Now, before we do that, we're going to be talking to Holly Evergreen and see what help we can provide. Hey, it's me, Holly Evergreen. My teacher has been locked out of the quiz database. Without access, the quizzes cannot be graded. So we need to get access back into that database. Okay, some hints about using PS. And so let's open up that terminal. Let's see. There we go. So we're talking about MongoDB. So first of all, we'll need to know how to connect to it. So that hint for using PS is definitely not bad. And we can see that Mongo is running on port 121212. So to connect to that, we'll use the following command, specify that port, and we have connections. Or we have connected. And now let's show the databases. LView, that looks like an interesting one. Admin might be interesting as well, but let's go for LView for now. So let's use that database, LView. So we switched. And now we need to know what collections are in there. So say show collections, the equivalent of a table in a relational database. And solution seems to be something that we would want to look at if we're talking about answers to quizzes. So let's find everything that's in solutions. And you did good. Just run the command between the stars. So let's grab that command, run that. And yes, that's a success. Perfect. So let's see what Holly has to say. Completely unrelated note, digital rights management can bring a hacking elf down. That elf scroll one can really be a hassle. It's good that Ron Bose is giving a talk on reverse engineering. Okay, so this is probably my favorite challenge of this year's CrinKleCon event or holiday hack challenge. Mainly because one, I am not good at crypto, but I learned a lot by looking at or watching Ron Bose's presentation, as well as trying to solve this particular challenge. So just to highlight, Ron goes over in quite a lot of detail how to reverse crypto. He starts off with all the components that you need to basically at the end follow along with a pretty complex example, but also the presentation itself is very useful for helping you out with the actual challenge. So let's see what we have in store, or what that challenge has in store for us. Objectives, and then recover Cleartext. The ELF Scroll tool is a vital asset used at ELF University for encrypting super secret documents. So we have the tool itself, which we can download. We have debug symbols, which we can download. And then we have an encrypted document, which we can download. And then we got some information about when the document was encrypted. So we probably will have to use that. And then we need to answer the question, what is the middle line on the cover page? We're looking for 5 words. Okay, so switching over to my Windows machine, let's start off by running that ELF Scroll binary and see what it does. So ELF Scroll, and then encrypt test.txt. I'm not going to give an output file, I'm just going to let it dump its output to the terminal. Oh, I obviously forgot a space there. There we go. So it shows us or tells us the seed value that it uses to generate the key. Then it shows you the generated key for that particular encryption, for that encryption run, I guess, for that run of that binary. And then it tells us a secret key after it has sent the encryption key over to the ELF Scroll server. The secret ID can then be used to retrieve the secret key or the encryption key from the server again, from the ELF Scroll server again, to decrypt the file at a later stage. So let's run that again. And let's compare the seeds. So we have one seed, and the second one is fairly similar except for the final digits. So it looks like this is most likely something like a Unix timestamp, epoch time. So let's mark this There we go. Let's go into the epoch converter. Timestamp to human date, and this is indeed the date and time that I'm recording this. Perfect. So we now note that we have an 8-byte length key. So we have that, and we know that the seed that's being used is most likely a timestamp. So now let's open up IDA. There we go. Let's create or disassemble a new file. All good. There we go. And back to this view. So what I want to look at first is, there's two things that I want to answer here. One is, well, how does the key get generated? What is the algorithm used to generate that key, so I can actually replicate that myself if I want to build a tool or write a script that actually decrypts the encrypted file. And secondly, I need to know what is the encryption algorithm that's used, that uses that key. So first things first, I'll go look at what's the function I want to look at? Generate key function. There it is. Generate key. So generate key does a few things. The first thing we already know. It calls time because it needs time as the initial seed value. So that happens first. That gets pushed into EAX. It actually says it in the comments. So looks like we're on the right track here. Then it runs super secure srand. Then it goes on, runs super secure random, and that loops for 8 times. So 8 times is gonna create or run that function. And so let's look at those things first. So let's see what happens in super secure srand as it's given that seed value. Nothing much. It basically pushes it into state. So seed is basically nothing more than the timestamp at that time. And looking at super secure random, that's a bit more difficult. That's doing more than just storing a value. So we have the seed in state. We see that state is pushed into EAX. Then we have multiplication of what's in EAX with this hex value, or if we translate this or convert this to this decimal value, then we add this particular hex value, or again this particular decimal value. Then we move what's calculated, and it's in EAX back into state, so that becomes our new seed value for the next round. And then we use that value of seed again, push it back into EAX, do a shift, right shift, 16 I think it is, yes, and then we do an AND operation with this value as well. So all of these things together is basically how we calculate the next seed value for when we get the next key byte, basically, as well as how that key byte itself is calculated. So based on the initial srand function, and then together with that random generator we have here, which is basically a pseudo random generator, since it's not truly random, it's always based on a timestamp, which we know and we can replicate. That's how we're going to solve this. We know this, so we can replicate how that key gets generated. Now, the second problem that we're trying to solve is what's the algorithm that's being used. And to do that, or to know more about that, we need to look at the do encryption. Where is that? Do encrypt. There we go. Gonna look at the do encrypt function, which has a few hints as to the algorithm that's being used. One is going to be down here in the comment, which says, well, crypt import key failed for des CBC key. So that's a hint, but comments can be wrong, obviously. So we're not quite sure if that's the case. The other thing that we can look at, though, is this value here, key blob header AI key algorithm. Because if you look for the crypt import key function, crypt import key, if you go down the line or down the page, you'll find the reference to key blob header AI key algorithm. And if you search for AI key algorithm, you'll end up in this page where they'll have all the possible values to designate what encryption algorithm you want to be using. And if you look at 6601, you'll end up with calc des. And that seems to be the exact value that we're using here. So our comment here seems to be confirmed by the value that's being set for that parameter there. So we're using des, where we also know what the algorithm is for the random function. We know what the seed is. So now we can basically replicate this in a Python script and then run that Python script to decrypt that file. So let's first look at that decrypt function, or that decrypt script that I've written. First of all, since seed is just the value as is, I'm not writing a function to store that. It's just simply, it starts off at 0, but then as I run through my script, I basically set that value, where do we go, where do we, as a global function, sorry, and then we start it off as we encrypt as well. I'll see that in a second. Anyway, rand function, as we mentioned, we take the value that's in seed, and then the new value of seed is going to be the old value that we multiply, and to which we add this value. That's going to be our new seed value that we saw in the function. Let's just really quickly check again. Subsecure random, there we go. So first we do a multiply, then we do an add. First we do a multiply, then we do our add. Then after that seed value gets stored, we shift that to the right, store that in value, and then we return next key byte as the value ANDed with that decimal value here, which is the same one as we have here in the code. So let's convert that, 32767, 32767. So that gives us our key bytes. Now to generate the key, we basically say, well, first of all, we're going to loop 8 times because we need to have 8 bytes. For each of them, we're going to generate a rand, and then this is some code I've added to get out the correct hex values, basically. And then finally, I join all of those values together to get the final key value. Now, the main function on what I'm going to be using for decrypting this, we still are missing one final piece, and that is we know how to generate the key. We know that the seed value is a timestamp. We know that the algorithm used is going to be des, but how do we know what the correct seed value is that we need to give our algorithm and our script to correctly generate the right key and then use that key to decrypt the file? Well, there's a hint that we're provided by, who was it again? Let's check. There's a hint that we get in the challenge, is that the file was encrypted on December 6, 2019 between 7 and 9 p.m. So that gives us a time range of possible seed values, 7,200 of them actually. And so we can convert that timestamp, that earliest time, into Unix time or into epoch time. We can use that as a base value, and we can loop over 0 to 7,200 and add that to that base value to go over all possible seed values to generate our key with. And that's what my script does. So we start off with the base value timestamp, which is going to be the equivalent of Friday, December 6th, 2019 at 7 p.m. Then for our range of 7,200 values, I'm going to add my key seed is going to be my start value plus whatever I'm looking at in that particular loop. I am going to generate my key with that particular key seed, which is going to start with this particular value, plus 0, but obviously it's going to be the same. Then I'm going to create my byte key out of what I generate. I'm going to define my cipher here. Then I'm going to open a file, my encrypted file that I'm going to read. And then I'm going to write that file or decrypt that file and write that to disk. Now, before I write it to disk, I'm going to first check what's in the first few bytes or the header and see if that's actually a PDF. If it is a PDF, we say pass, it decrypts to a PDF, we write it out to a file, and we break out of that loop because we don't need to check anything else. We were successful, and otherwise we just continue on because that particular seed value was not the correct seed to correctly decrypt that file. Now, it takes a while to actually run the script, so I'm not going to run it for this particular presentation, but I will show you the output because I just ran it before I started recording. And so let's see if I scroll up. Don't want to scroll. Make sure there we go. Oops, that's too far. That's my other output from my previous presentations. There we go. So as I run the script, it basically starts with 0, and this is for the first epoch timestamp basically, and that is not good. But if I go all the way back down at value or loop number 4850, that is where I actually get a good result, and it decrypts the PDF. The fact that we now know the iteration that it is successful, we also know the exact timestamp on when that file was decrypted, namely our base epoch timestamp plus 4850, which is going to give us our correct time up until the second. So that decrypts that file, and that file then looks like the following. If I can grab that, there we go. And it looks to be like a manual or a quick start guide for the machine learning sleigh route finder, the Super Sled O-Matic. Side note, as with everything in KringleCon events and Holiday Hack Challenge events, the level of detail that's being put into these challenges is pretty astounding. This manual itself is hilarious to read as well. So if you have time, definitely go through that. You would have to do actually, because in future challenges, you actually need some information that is in that file. We'll look at that later. So looks like if we go back to the objective, what is the middle line on the cover page? Hint, it's 5 words. Well, let's go look at those 5 words. 1, 2, 3, 4, 5. Looks like machine learning sleigh route finder. So copy that and then paste that in here and submit, and it looks like we found it. It's correct. Perfect. Well, that's it for this episode. Looks like we have, let's see, 2 more to go. Hope you enjoyed this one. This, like I said, was my favorite out of this year's challenges. Hope you did as well. I hope to see you as well in one of the next episodes. And until then, thank you very much for joining. Goodbye.